So Kruskal'S algorithm, developed by Joseph B. Kruskal in 1956, is a greedy method used to find the minimum spanning tree or MST of a connected, undirected weighted graph. So to break that down, Kruskal'S algorithm is a method used to find the most efficient way to connect all the nodes in the graph with the least total weight. It's especially used in situations where the graph is sparse, meaning it doesn't have too many connections. The key idea is pretty straightforward. It starts by sorting all the edges based on their weights, from smallest to the largest. Then one by one, it adds the smallest edge that doesn't create a loop, and it keeps doing this until all the nodes are connected. What makes Kruskal'S approach powerful is that it doesn't care about any existing path, wherein it just focuses on finding the next shortest link that connects new components. This independent step-by-step method makes it simple and efficient, especially for smaller or spread out graphs. However, it can slow down with really large graphs because sorting all those edges takes time. Still, it is a classic and widely used algorithm that plays an important role in the fields like network design, where building the shortest, cheapest connection is critical. So now, we're going to the algorithm overview. Kruskal'S algorithm is used to find the minimum spanning tree of a connected, undirected, and weighted graph by selecting the lowest weight edges. It begins by sorting all edges in ascending order based on weight. Then, it adds edges one by one to the MST, ensuring no cycles are formed using a union-find data structure to manage connected components. The algorithm stops when all vertices are connected, resulting in a tree with a minimum total edge weight. To explain briefly, Kruskal'S algorithm builds the minimum spanning tree by always picking the lightest edge available that doesn't create a cycle. It keeps track of connected components using union find, which helps prevent loops. The process continues until all the nodes are connected, giving us the most efficient network in terms of total edge weight.
Next is the big O notation. Kruskal'S algorithm has an overall time complexity of OA log E, where E is a number of edges in the graph. This is mainly due to the initial step of sorting all the edges by weight, which is done using efficient algorithms such as merge sort or heap sort, both operating in OA log E time. The difference between merge sort and Kruskal'S algorithm is the merge sort is a method that arranges a list of numbers by splitting them into smaller parts, sorting those parts and combining them back into one sorted list. And the Kruskal'S algorithm is find the shortest way to connect all the points in a graph by first sorting the edges by weight, then picking the smallest one by one, making sure no loops are formed. After sorting, the algorithm uses a union find data structure to check the cycles of merged sets. This is operation run into almost constant time due to the optimization, especially the OAV per operation, where a least inverse increment function, and the V is the number of vertices. Since AV grows extremely slowly, it is treated as a constant in a practice, making the union find step in run in a OA time overall. Therefore, since the sorting step dominates the total time complexity of OA log E, it is also be written as OA log V, using the fact that E is often related to V, especially in sparse graph. Union find operation are the parts of data structure that use efficient manage disjoint sets, group of elements that don't overlap. It is especially useful for Kruskal'S algorithm to avoid the cycles when building a minimum spanning tree or MST. So that's all. Thank you.
So now, let us proceed to the real-world simulation of Kruskal'S algorithm. Kruskal'S algorithm was applied to a highway inspection system modeled as a weighted graph, where edges represent roads and weight denotes distances. The simulation involved sorting edges by weight, iteratively adding the shortest non-cyclic connection. and achieving an MST or minimum spanning tree with a total weight of 61 km. This demonstrated the algorithm's efficiency in optimizing real-world pathfinding tasks. In this simulation, I'll be demonstrating a real-time simulation of Kruskal'S algorithm. Using our campus map, the goal of Kruskal'S algorithm is to find the shortest possible way to connect all points. In this case, buildings without creating any loops will walk through the simulation step by step. In this scenario, we selected 7 buildings and assigned them the labels. From starting point A, idle building 1, destination B, IT building 1, C for IC building, D for library building, E for administration building, F for covered court, and lastly, the endpoint is the IT building 2. Then, we connected these buildings with edges representing the roads between them. Each edge was assigned a weight representing the distance in kilometer. Right now, I'm walking from starting point A, which is the ILIC building, and I'm going to destination B, IT building 1. This edge has the lowest weight, or shortest distance, which is just 1 kilometer. According to Kruskal'S algorithm, we start with the smallest edge. Next, I am going from B to C, or from IT building 1 to the IC building. This edge is 2 km, and since it doesn't create any cycle, we add it to our minimum spanning tree. Now, I am walking from C to D, or from IC building to library building. This path is 3 km. Again, it connects a new building and doesn't form any loop, so we include it. I'm now on the way from D to E, or from library building to the administration building. This path has a distance of 4 km. We're still following Kruskal'S logic of choosing the shortest available path that doesn't make any cycle. Next, I am walking from E to F, or from the administration building to the covered court. Now, this connection is 6 km, and it continues to expand our spanning tree without forming any cycle. Lastly, I am walking from F to G, or from the covered court to IT building 2. This final connection is 5 km, and now we've successfully connected all 7 buildings while following Kruskal'S algorithm. So now, we've walked through all the connections chosen by Kruskal'S algorithm in this simulation. The total distance traveled was 21 km, and this simulation shows how the Kruskal'S algorithm helps us connect all necessary points with the minimum total distance, or the MST or minimum spanning tree, so making it perfect for real-world use like campus, navigation, and system optimization. And that's all about the real-world simulation of Kruskal'S algorithm. We are now at starting point A. Let's go to destination B. We are now at starting point B. We are now at destination B. Let us go to destination C. We are now at destination C. Let us go to destination B. We are now at destination B. Now, let us go to destination E. We are now at destination E. Now, let us go to destination F. We are now And now, we are at our destination G, which is our endpoint.
The video demonstrates Kruskal'S algorithm by showing how it builds the shortest path through a network by always choosing the smallest available edge that doesn't form a cycle. From the beginning to the end, it connects all points using the shortest possible links, highlighting the algorithm's goal of minimizing total distance. This shows that the way to walk from the start to the end is always the shortest through the selected connections.
Mao ni ang among array length sa Kruskal'S simulation. Mao ni siya, 6 lang siya kabuok. So before ko mag-start, gusto na ko i-discuss kung unsa ni sila. So first, kaning 6, kanila akong example, pinakaiwit. Ang 6 kay mao na siya ang starting point. While kaning number 1, mao na ang destination. While kani, mao na siya ang from starting point to destination, mao na siya ang kalayon. So tawagon na lang nato na siya distance. So, para ma-visualize nato ang unsa kalayaon or kanang simple visualization lang. So, pwede ka mo gamit bisag unsa na pattern, pero akong gamiton lang na pattern is circle. So, just like this. So, mo ni ang number 1, mo ni number 2, 3, 4, 5, and 6. So, unahan na to ang number 1, of course. So, 1. So, magbuhat na kong pattern. Ingani lang. 1, 2, 3, 4, 5, and 6. So, tanga na itong dot. So, just like this. So, mauning starting point to destination. So, ato siyang i-align. So, from starting point to destination. S and D. And, di ba, 1 and 3. Starting point and destination. So, ang distance niya, mauni nagsilbi ang line, which is 1. So, tawagon na to siya this. So, continue. Number 2. Pattern. 1, 2, 3, 4, 5, and 6. So, 2 and 5 again. Starting point 3, destination 5, distance 2. So 3 and 5 here. So this is 2. So again 3, so 5 starting point, 2 destination. So 5 and 2. The distance is 3. So 4. 1, 2, 3, 4, 5, and 6. 4, 2 starting point, 4 destination, 2 starting point, 2 destination, 2 starting point, 4 destination, and 4 distance. So, 2 to 4. So, this is 4. Now, let's proceed to number 5. 1, 2, 3, 4, 5, 6. 4 to 6. 5. Number 6, the last number. 2, 3, 4, 5, 6. So, destination ay starting point 6, destination 1. So, the line will be 6. So, buhaton na to siya tanan, like, isaho na to siya og pattern, like, naka-combine na gud sila tanan, kay dapat ingana mo dapat. Pero ginganin ako at first, because gusto ko kanang sabotable, dili libog. So, try ako siya buhaton. Wait lang. I will make a big pattern. Combination. Kruskal'S. So, 1, 2, 3, 4, 5, and 6. So 1, 2, 3. This is 1. 3 to 5. Here. This is 2. 5 to 2. This is 3. 2 to 4. This is 4. 4 to 6. This is 5. And 6. 6 to 1 is 6. So, this is the pattern of this array length of Kruskal'S. So, ang i-avoid lang nato aning Kruskal'S is dapat ang iyang pattern dili siya circular ang pagkuan, ang iyang buo, like okay lang zigzag, basta i-avoid na to ang circular. Don't allow circular pattern. You should know that, guys. So this is the combination and this is the individual of each of these.
So hello everyone, this is Gean, and today I will be showing you our data algorithm assessment video of the code that we are giving in the given examples, so that I will discuss this code and teach you the algorithm for this code. So in the previous members of my previous other group members, you have already discussed insight about Kruskal'S MST, like minimal spanning tree and vertices as cities and edges as roads. So first of all, we have a class of data algo final branch. This is our main class, and it holds the main method that is crucial for the algorithm, which is Kruskal'S MST minimum spanning tree, and it holds parameters like vertices and a list called edges. So collections that sort. So let's just say na this code right here, collections that sort, is a utility, and And we imply the parameter right here, which is the edges, which indicates the list edges, the list that is called edges, which means our given, which I will also discuss later. So we have a union find. Union find, we instantiated an object, union find, which is also at the class edge class. So union find UF, this is right here, this is union find. Union find, we instantiated it as UF equals new union find that holds parameters vertices, which also tackle later. And so we have int total weight is equal to 0, instantiated a new variable total weight is equal to 0, so every time we call Kruskal'S method, we have total weight is equal to 0. So system out print edges and MST. So for we have printed edges and MST. So for class edges, it means that for every edge in class edge edges, which is this list right here, we put it in the edge variable. And if UF, this code right here is basically saying if another city is not equal to the current city that we are comparing it to, then this code right here will run. So that's how the cities merge together, and they merge on something called union method, which is this method right here that puts the current cities and the previous cities that we encountered dependent on their edges, which is the weight. That means the distances of the roads. Dependent on their weight, we can actually determine the most. We can determine their most least distances possible at the same time connecting all cities. So after we call Kruskal'S method, so we return total weight. So total weight is equal to plus equal to edge dot weight. So how do we read this? So total weight is equal to total weight plus edge dot weight. So if this statement is true, then that means we are saying that the current city plus the city current that we are comparing it on, once they will merge, their weight will also merge and put it in this total weight. So we also have system of print in road from edge source, and the destination, which is the city that we're comparing it to, or the group that we're comparing it to, is equal to have the current weight of the roads. Then those current weights of each those cities or groups would put in the total weight variable, and every time this method is called, then we return the total weight, which is also the Kruskal'S method is called here. So let's go in here. Public static void run test case. So this run test case right here is our method for running tests on our given edges. So we have a parameter test case number, vertices, and the list called edges, which holds edge. So system out print in test case number is just like our primary ID, so don't focus on that. So in total is equal to Kruskal'S. This is the thing that I am saying earlier. It returns total weight, so that means the total weight from the given vertices and edges that we will give is now stored in this variable total right here. So system out print in, so that means in every time we run test case, we will have this total distance of MST, this total, we get the total value of its edges, which we gave an example of kilometers. So in the main string, we have 3 examples, but we're just going to focus on one, edges 2. So these are its edges. These edges that we instantiated each class edge in the class edge list. So class, just for example, this list in the class edge, we named it class edge 2. We stored class edge 2 here when we run test case. So let's say for example we run this is the test case 2. Run test case, primary ID of 2, and 5 vertices, then edges of 2. I mean edges 2, that's just the name. So edges 2, store these values right here. That means when we run test case, 2, 5, and edges 2, right here, this case number is 2, vertices is 5, edges 2, that means this right here is also stored here in the list of edges. That means system out print in test case number is equal to 2, then int total is equal to Kruskal'S vertices and edges, which we'll also tackle later. System out print in total distance of MST, you already know that, so let's go dive into the class edge and its deeper understanding. So in this for loop right here, this is the main reason how we could get these values of the total indexes and how we group them in this algorithm, Kruskal'S algorithm. So we have these values, given values, new edge. So let's say we actually have 5 cities, 5 vertices as well. That's obvious because we already gave that. And our indication is that we have 0 to 4. We have 0 to, let's say for example, city 0 to city 1, we have a road kilometer of 2. Then city 0 to city 3 is 6, city 1 to 2 is 3, then so on and so forth. So in this algorithm, first when we call Kruskal'S MST method right here in run test case, which is this, it actually sorts the edges, and so that it would read it as dependent on its edges, which is also indicated here. This is the reason why our Java code knows that we should compare it by its weights. Like this, that weight, current weight is equal to minus other that weight from other edges. So we sorted it out. So our code knows to sort this in a manner like for its weights, which is, let's start from 2, then 3, then 5, 6, 7, 8, and 9. So that's how it is. And union find, instantiation, total weight, you already know that. Let's hit here's a for loop. So for every class edges, which indicates this list of edges called edges, the list is called edges. Then we put the values in this variable edge. That means if UF that find edge, so we are comparing this for every class edges, we are basically comparing all of these values. So that means we are looping through every edge. And then let's start with UF. So UF that find edge SRC is not equal to UF that find edge that destination. So that is actually here. So in the find statement, UF that find. So basically it's like saying that if a group of cities is already have the same root, let's for example the lowest weight is the root, which is 2. If they already have 2 in their groups, then that means this is they should merge, this is true. I mean, if the source destination of the edge, and we are going to compare it to its destination, if those doesn't actually if edge that source is not equal to find edge that destination, then it will run this code, which is union, which is the merge part method that merges their groups, means their cities. And every time that they actually merge cities, their total weight also merges and prints out road from its current city to its compared city. So let's say for example city 0 and city 1, so source destination, if city 0 is not grouped to city 1 and they aren't connected yet, their roots aren't connected yet, then that means we are going to run this code right here inside the if statement. Then that means those cities, which is city 0 to city 1, is now merged. And if we do this to every comparison in the edges that we have instantiated right here, that means when the for loop ends, those total weights would their weights, which is the distances, would actually equal to total weight. It's like calculating the weights and return total weight value until we get our shortest total of kilometers. So we're gonna try to run it, and test case, this will run first. Yeah, this will run first. Test case number 1, test case 2, test case 2. Okay, test case 2, edges in MST 0 to 1, yes, 2 kilometers. We can see that here. 0 to 1 is 2 kilometers, which is here. Source, destination, and weight, which is 2 kilometers. And total distance of MST is 16, and they already knew that they cannot include other vertices or other cities if they are already connected in their groups. So that is how the algorithm works.
Results and observations. Kruskal's algorithm successfully generated MSTs in all cases, with strength and simplicity and cycle avoidance. Based on the result and observation, we can see the Kruskal's algorithm performed very well in generating minimum spanning trees. One of its major strengths is simplicity and natural ability to avoid cycle during the process. It consistently produced correct result in all test cases. However, one noticeable drawback is time it takes to sort all edges before building the MST. These steps becomes a bottleneck in larger graphs, making Kruskal's slower compared to algorithms like Jakarta's when dealing with high edges density. So overall, the algorithm is ideal for sparse graph and scenarios where minimizing complexity is important, but does not face some limitation in terms of scalability and speed when applied to larger, more connected networks. In conclusion, experimental results show the algorithm performed exceptionally well on sparse graphs, completing MST construction for 1000 nodes in just 120 ms. However, performance degraded noticeably on dense graph, with execution time increasing in 350 ms. For complete graph, memory usage analysis revealed a linear graph pattern with respect to edge count. The algorithm consistently produced 100% accurate MST, matching theoretical prediction. This finding confirmed its reliability for typical network optimization tasks while highlighting specific use cases where alternative might be preferable. In summary, Kruskal's algorithm is fast and reliable for sparse graph with perfect accuracy. However, it slows down on dense graph, making alternative better in those cases.